We're surrounded by these invisible forces, right? And two of the biggest are electricity and magnetism. Now, we usually learn about them as two totally different things. You've got static electricity over here and magnets on the fridge over there. But it turns out that's not the whole story, not even close. There's a hidden connection, a deep secret that, once we figured it out, completely unlocked the modern world as we know it. Okay, let's break this down. On one side of the ring, you've got electricity. It's all about electric charge, right? Charges create electric fields, and those fields push and pull on other charges. Simple enough. Then, on the other side, you have magnetism. That's all about north and south poles creating magnetic fields that act on other magnets. They seem to live in their own separate worlds, playing by their own rules. But here is the one simple question that changes absolutely everything. What if that charge isn't just sitting still? What if it's moving? The moment that charge starts to move, it completely blurs the line between those two separate worlds, and it reveals a secret about how our universe is put together. This is where things get really interesting. So let's get into our first big idea. You know, this whole revolution in thinking didn't start with some grand, complicated theory. Nope. It started with a complete accident during a classroom lecture. It was totally by chance. Picture this. Oersted is in front of his students, showing them how an electric current can heat up a wire. And he just happens to notice a compass sitting nearby. Every single time he flips the switch and sends current through the wire, the compass needle twitches and points away from north. That was it. That was the first hard proof that an electric current, moving electricity, creates its own magnetic field. The two forces weren't separate after all. And that's really the first half of this big secret. Magnetism doesn't just come from those clunky magnets you have. Any moving electric charge, any current at all, wraps itself in a magnetic field. A charge that's just sitting there has an electric field, sure, but the moment it starts moving, a magnetic field just blossoms into existence all around it. Motion is the key that connects these two forces. And what's so cool is that there's a really simple trick to visualize this invisible force. It's called the right-hand thumb rule. If you imagine a wire with current flowing through it, just point the thumb of your right hand in that same direction. Now, curl your fingers. See how they wrap around the wire? That's it. That's the direction of the magnetic field. It's an incredibly simple and powerful way to see the unseen. Okay, so we've established that moving charges create magnetic fields. Well, you know, physics just loves symmetry. It pops up everywhere. So it only makes sense, right? If a moving charge can create a field, then a magnetic field should be able to push back on a moving charge. And, well, it absolutely does. And this interaction follows a very clear rule called the magnetic Lorentz force. The push that a charge feels really comes down to three things: how much charge it has, its Q; how fast it's moving, its velocity V; and how strong the magnetic field is, that's B. The more you have of any of those, the stronger the push. But here's where it gets really specific. The field doesn't just push on any moving charge. There are rules. If the charge is sitting still, nothing. Zero force. If it's moving perfectly parallel to the magnetic field lines, kind of like a car staying perfectly in its lane, again, nothing. The force only shows up when the charge cuts across the field lines, and you get the biggest possible force, the maximum push, when it cuts across at a perfect 90-degree angle. And just like we had a rule to figure out the field's direction, we have another handy trick to figure out the direction of the force. This time, it's Fleming's left-hand rule. You just use your fingers to represent the field and the current, and your thumb magically points in the exact direction that charge is going to get pushed. It's like having a little physics calculator built right into your hand. All right, so let's put all these rules together, because this is where the physics stops looking like equations and starts looking more like art. We can now predict the exact path the charge is going to take as it flies through a magnetic field. Now, this next part is maybe the most important and kind of weird thing to get. The push from this magnetic field, it's never forwards. It's never backwards. It is always 100% of the time sideways. It's always at a perfect right angle to the direction the particle is already moving. So just picture it. You've got a charge flying along in a perfectly straight line. The second it hits that magnetic field, bam, a force grabs it and yanks it sideways. So it starts to turn, but the force immediately adjusts, always staying perfectly sideways to its new direction of travel. It's a constant, relentless sideways push. So what happens when you have a constant sideways force? Well, it forces things into a circle. It's exactly like swinging a ball on a string around your head. The string is always pulling the ball towards the center, a sideways force, and that's what keeps it in orbit. The magnetic force acts just like that string, and because it's only pushing sideways, it can't speed the particle up or slow it down. All it can do is steer. It provides a perfect centripetal force. So the end result of all this is pretty amazing. The particle gets trapped in this perfect circular dance, endlessly orbiting the magnetic field lines. Its speed never, ever changes. And because its speed is constant, its kinetic energy is also constant. The magnetic field does zero work. It's like the ultimate cosmic shepherd, effortlessly guiding its flock in perfect circles without ever getting tired. But what if the particle doesn't come in perfectly perpendicular? What if it enters at an angle? Well, then you get this absolutely beautiful spiral. Part of its motion is used to make the circle, and the other part keeps it moving forward along the field lines. The result is this gorgeous helical dance, a particle just corkscrewing its way through space. Okay, so we have this beautiful circular dance, but who cares, right? Why does this matter outside of a physics lab? Well, it matters because this one single fundamental force is the engine that drives pretty much every electric motor on the planet. Let's zoom out for a second. Instead of one single charge, let's think about a whole river of them, a current flowing through a wire. Now, if you put two of these wires next to each other, the magnetic field from wire 1 will push on all the moving charges in wire 2, and vice versa. And it turns out, if the currents are flowing in the same direction, the wires actually pull towards each other. They attract. If the currents are in opposite directions, they push each other away. They repel. So how do you get from two wires tugging on each other to an actual spinning motor? Well, an electric motor is just a super clever application of this exact same force. Instead of a second wire, we use powerful magnets to create a strong, steady magnetic field. And instead of a straight wire, we use a loop or a coil. The field pushes on one side of the coil one way and on the other side of the coil the opposite way. And that creates a continuous turning force, a torque, that makes the whole thing spin. So look, the bottom line is this. This isn't just some abstract concept. Every single time you turn on a fan or a blender or you drive an electric car, every one of those devices is working because of this principle. They are all just brilliant machines designed to harness that fundamental push between magnetism and moving charges to create motion. Okay, let's just take a step back for a second and appreciate what a truly huge idea we've just unpacked here. I mean, think about it. We started with two forces that seemed totally separate, electricity and magnetism. Lived in different houses, had different roles. But we discovered that they are completely connected. Moving electricity creates magnetism, and magnetism pushes back on moving electricity. They're not two different things. They are two sides of the exact same coin. A single, fundamental force of nature we call electromagnetism. And that, of course, leads to the next huge question. We've seen that moving electricity can make magnetism, but can it work the other way? Can moving magnetism create electricity? Well, the answer to that question is the key to the other half of our entire electric world, how we generate power in the first place. But that revolutionary discovery, well, that's a story for another time. Thanks for watching.